by n matrix, and we have these things called the column space and the row space. Well, what do you think they are? What do you think? Pretty clear, maybe, Devin. What do you think the column space is going to be?
Column space is the columns in the matrix.
It's not just the columns, but the whole. If you take the columns and you use them as you take the span of the columns, then you get the subspace. Okay, so it's a subspace generated by the columns. So we call the span of the columns A1 through AN, right? And notice that this is in Rm, right? Because each of these guys, is an m by one matrix. We call these guys the span of these guys the column space of A, column space of A, and we call the span of the rows A1 through AM the row space. So just what you would guess, right? You take the columns and you take their span. That's a subspace called the column space. The span of the rows is called the row space. There's a third definition. We call the dimension of the row space. The dimension of the row space of A is called the rank of A. The rank of A. Okay, so the dimension of the row space, right? The number of guys in the basis. Okay, so let me ask you a question. Suppose you have the row space. Suppose you have a matrix. Suppose you have a matrix, and you do an elementary row operation on the matrix. Have you changed the row space? If you switch two guys, do you change the row space? No. If you multiply somebody by a scalar, do you change the row space? No. If you add one to another, no. Right? Because you're not changing the set of linear combinations. Right? So elementary row operations don't change the row space. And so what you see is that if you have two matrices and they're row equivalent to each other, then they have identical row spaces. Okay, right. So if you have row equivalent matrices, then they have the same row space. Okay. So for example, if I take a matrix 3, negative 3, 1, 3, 4, 1, 2, negative 1, negative 2, negative 3, 8, 4, 2, and I do Gaussian reduction on it. Suppose I do Gauss-Jordan reduction on it, blah, blah, blah. I end up with, say this, I'm sorry, just doing Gaussian elimination. So 1, 2, 1, negative 1, negative 2, 0, 7, 0, negative 2, 0, 0, 1, 0. Okay. So you see that what do you see? Let me change this to like this, just to make it clear. Okay. Well, then these guys are going to have identical row spaces, right? These guys have identical row spaces. Right? That is, the row space of this is the same as the row space of this. In other words, it's the span of these three matrices, these three vectors, right? If I call this thing A, the row space of A is just the span of these three vectors: 1, 2, negative 1, negative 2, 0, 1, 0, 1, 0, negative 2 sevenths, and 0, 0, 1. Okay. And so you see that the rank of A is 3. The rank of this matrix is 3. Right. The rank is the dimension of the row space. We did this thing. It turned out to have 3 guys in its basis. And that's it. Okay. Any questions so far? Any questions? Yeah, Ross.
Just a quick question.
Yeah.
Because for the dimension, should we check the linear independence?
That's what's happening here, right? So if it turned out when we did the row reduction, maybe one of the rows would get eliminated. That would mean that the third guy was dependent on the other 2.
So you actually already checked it.
That's what's happening when you do your row reduction, right? That will happen,
Okay.
right? So as long as you reduce down to row echelon form, then that will tell you, right? So we could have lost one on the way, and then we would have said, oh, this thing looked like it was 3-dimensional, but actually it's 2-dimensional. Okay, so this is the way you figure out the basis, right? So this thing here, we get a basis for the row space of A. Right? We started off with this thing. We don't know how many dimensions it has. We come down to here and we say, oh look, these guys are all linearly independent, right? These guys are all linearly independent, and so these guys form a basis for this guy's row space. But this guy's row space is the same as that guy's, and so this gets us a basis, right? So that, yeah, right. So we can determine a basis for the row space of A by Gauss-Jordan reduction. Gauss-Jordan reduction and Gaussian elimination. Okay. Right. And what you see is that the dimension of the row space is the same thing as the number of pivots. The same thing as the number of pivots in the reduced form. Okay. So the rank turns out to be the same thing. So notice that rank of A turns out to be the number of pivots. Right? The number of pivots in the row echelon form. Okay. Okay. If we went on a little bit, let's go one step farther. Okay. So continuing, this A, if we go all the way down to the reduced row echelon form, looks like this: 1, 0, 0, negative 10 sevenths. 0, 1, 0, negative 2 sevenths, 0, 0, 1, 0. Okay. Take 1 minute and tell me what the row space is. I'm sorry, the null space. So calculate the null. Take 1 minute just for practice and calculate what the null space is. Okay. Somebody tell me how to get it. Somebody want to tell me how to do it? Lizzie?
I got 0, 0, 0, 0.
0, 0, 0, 0.
Wait.
So remember, right, what does this say? This says that x1 minus 10/7 of x4 equals 0, right? x2 minus 2/7 x4 equals 0. x3 equals 0, right? And x4 is just whatever.
Sorry.
Okay, so remember, right, so what is the null space? Right, so what does the null space look like? Well, right, it'll look like 10/7 x4, 2/7 x4, 0, 1, but 0 x4. Right, anything that looks like that is a solution. Right, we can pull the x4 out, right, and just call it some number s. Okay, so the null space look like this. The null space looks like this, and you see that the dimension of the null space is 1, right? The so-called nullity is equal to 1. Okay. Right, and what you see is that right, x1, x2, right, and x3 were your lead variables, and there was one free variable. Right? x4 was a free variable. Right? Yeah, read.
So, haven't all the systems we've done before have had a nullity of 1? Because we always express it as 1 vector.
No, we've had examples where there were two, like the first two were lead and the second two were
because it's
free.
just like the number of free variables.
Yeah, it's the number of free variables,
Okay.
right? So what you see is that the nullity is the number of free variables,
Okay.
right? Okay, so nullity turns out to be number of free variables, right? And what you see is that there's some relation between the rank. What's the relation between the rank and the nullity? Can anyone see this? If you've read it, go ahead and say it. If you haven't read it, I'll be impressed if you just see it. What's the relation? There's some relation between the rank and the nullity. Lizzie, go ahead.
Wait, okay. No. Is the rank plus the nullity the number of columns?
The rank plus the nullity is the number of columns, exactly. And so this is the rank theorem. I give you 2 points on the next exam for that. Or maybe 3. 3 points on the next exam for that. Good. Right, so this is the theorem called the rank theorem. That if you have a n by n matrix, then the rank plus the nullity equals the number of columns n. Okay. And the proof basically is exactly what we did in this example, right? What do you notice? You notice that the rank, right, is the number of pivots, right? The number of pivots is the number of lead variables, right? Number of pivots, same thing as the number of lead variables, right? The nullity is the number of free variables, right? Nullity is the number of free variables, right? So the rank plus a nullity is just the number of variables. In other words, the number of columns. Okay. So you just take, the proof is basically just use do Gauss-Jordan reduction. And then just observe that the dimension of the dimension of the row space is the number of lead variables, and the dimension of the null space is the number of free variables, and those two are the number of variables together. That's it. Yeah, Julia.
And this is helpful because the rank is usually something that we don't have to have about. I mean, if you're going to find the null space,
Yeah.
you usually need the vectors. It's usually more helpful to have the actual vectors that comprise the null space than just have the dimension of the null space, correct?
Yeah.
So you would use it more to find the rank. You would use this theorem more.
You could use it either way, actually. So if you have the rank, then it will give you the nullity. If you have the nullity, it gives you the rank.
But what help is it to know the dimension of the nullity?
Let me give you a problem. You're sort of playing into my hands here. I have an exercise for you to try. So here's exercise 24. Try this. Take a couple minutes and see if you can solve it. Suppose you have two square matrices, and you know that the null space of their difference is Rn. Then they must be the same matrix. So think about this for a minute in the context of the rank theorem. Right? How would you show that these matrices have to be identical? If the nullity of their difference, if the null space of their difference is all of Rn, then what does that tell you? Or actually, sorry, let me start off with an easier one, or one that sets it up better. Sorry, number 10. Let A be an m by n matrix, and say that the rank of A is n. Suppose that AC equals AD. You've got these two vectors, and A times the first vector equals A times the second vector. Does that imply that C and D are the same? Does that imply that C and D are the same? If A times the vector, A times C equals A times D, does that mean that C and D are the same? Okay. So take a minute or two and see if you can figure it out. Okay, talk with somebody nearby. Turn to somebody nearby and talk with them please about this. Nico, talk with them. You guys want to
Nullity is 0.
I don't know what that implies. I'm assuming yes.
Sides by A inverse.
Yeah, that would also definitely be the same. Yeah.
Does free grading just like reduce a degree of
This step is this nullity equals 0.
Okay, anybody want to say something? Anybody want to say something? I see some nodding heads. Reed, go ahead.
So we said that if the rank plus the nullity equals n,
Yeah.
and the rank also equals n,
Yeah,
then the nullity equals 0,
yeah.
which means that A has to be invertible, so you can multiply both sides by A inverse.
Okay, great. So yeah, by the rank theorem, we know that the rank plus the nullity equals n, but the rank is n, so the nullity is 0, right? That means that the dimension of the null space, in other words, the dimension of the null space is 0, right? But that means that, hold on a second, we cannot say this is an invertible matrix because it's an m by n matrix.
Oh,
Okay, so no.
Yikes.
But if it were a square matrix, then yes.
okay.
Okay, but you're really close, right? You say, well, look, the null space is 0, right? The null space is 0, right? The null space is only the 0 matrix, a 0 vector, right? Can anyone see? Did anyone get any other way of seeing it? Yeah.
You subtract both sides by a times c, and then that equals 0. So you can factor out the a,
Yeah.
and d minus c has to be 0.
Okay, great. Yeah. So you say, okay, well, look. Well, you also know that AC equals AD. AC equals AD. So let me move this up. Say, well, AC equals AD, but that tells you that AC minus AD equals 0, the 0 vector. But that means, distributing out A times C minus D is equal to 0 vector, right? In other words, C minus D is in the null space, right? C minus D is in the null space, but the null space was just the 0 vector, right? The null space consisted only of the 0 vector, so C minus D must be the 0 vector. In other words, C equals D. Okay. Okay, so C is equal to D, right? C minus D must be 0. In other words, C equals D. Okay. Any questions about that? Okay. What if, this is actually part 2 of the question, what if the rank was less than n? What if the rank were less than n? Then would C equal D? Would C equal D? If you had that the rank was less than n, right? If the rank is equal to n, then C has to be equal to D. Okay. What if the rank is less than n? Can anyone see what would happen? Does C have to be equal to D? No. No, it doesn't, right? Because all it would say is that C minus D is in the null space. But the null space wouldn't be the 0 vector anymore. The null space would be some subspace, right? All you know is that C minus D is some element of the null space, C minus D is some element in the null space. Okay, that's actually kind of useful, right? That's saying that C equals D plus some for some element of the null space. Right? That they differ, like that C they're going to differ by some element of the null space. So that's not useless information. That's information, right? But it's not, maybe it's not as pretty as the first part. Okay, any questions? Any questions? Okay, so yeah, it's just that you guys seem so dead. You get enough sleep? Get more sleep. Get more sleep, or wake up earlier. Those are contradictory. Those are contradictory, but do them both. Those seem to be contradictory, but actually they're not. Okay, so here's the question. I was commenting to another professor that the best class I think so far in this term has been the class where I had you running around hitting each other with a newspaper bat first, right, and then had lecture. Right? You were most alive at that time. How come we don't care? We don't care about the dimension of the column space. How come we don't care about the dimension of the column space? Well, turns out that the dimension of the column space is the same thing as the dimension of the row space. In other words, the rank, it's the rank. The dimension of the column space and the dimension of the row space are the same. So the rank is equal to both of them. Yeah, Dan?
So does that mean if we took the transpose of a matrix, the rank would still be the same?
That's right.
Okay.
That's right, yeah. So, yeah, yes. Yeah, so if you wanted to find the base, so you know how to find the basis of the row space. You do a Gauss-Jordan reduction on it, and you get those linearly independent rows, and that would give you a basis for the row space. If you took the transpose and did Gauss-Jordan reduction on it, you get something that would give you a basis for the column space. And we see that those actually have the same dimension. Okay. So proof. So let's recall something that we know very well, that if A and U are row equivalent to each other, then AX equals 0 if and only if UX equals 0. Right? The solution set doesn't change. The solution set of this problem, of this equation, is the same. Of these solution set of these equations are the same. Right? Of course. Right? Okay. That's something that we've talked about, over and over since the very beginning, like the first day of class, basically. Okay. Now, let's think of this from a different viewpoint. What is this saying? This is, if AX equals 0, that means that x1, a1 plus x2, a2 plus blah, blah, blah equals 0, right? If ux equals 0, that says that x1, u1 times the first column, x2, u2, blah, blah, blah equals 0, right? So what this is saying is that if there's some dependence between the columns here, the columns of A, then there's a corresponding identical dependence between the columns of U, right? Right. This is saying that this says if x1, a1 plus xn, an equals 0, that happens if and only if x1, u1 plus xn, un equals 0, right? Of course, the dependencies between the columns are the same, right? Any dependence, any linear dependence between A's columns is a dependence between U's columns, and vice versa. Right? Let me give you an example just to make that more concrete. So we'll get. So I'm going to cut out of the proof for a second just to give you an example, and then we'll come back. Okay. So if we take a matrix A being 1, 2, 2, 3, 2, 5, 4, 8. -1, -3, -2, -5, 0, 2, 0, 4, and we reduce it down to its reduced row echelon form. It looks like this: 1, 0, 2, -1, 0, 1, 0, 2, 0, 0, 0, 0, 0, 0, 0, 0. Okay. If we do Gauss-Jordan reduction on it, then we see this. Okay. Everybody watch. Everybody take a look. Okay, stop copying. Take a look. Okay, look. So now notice something. If I look at this last guy, this column is twice this column, right? This is 2, 0, 0, 0. This is 1, 0, 0, 0, right? Now you look. This column is twice that column. 2, 4, 2, 2, 4, -2, 1, 2, -1, right? This guy here is -1 of the first guy plus 2 of the second guy, right? I take -1 of the first guy, 2 of the second guy, add them together, and I get this guy. Right? And you see that if I take -1 of the first guy plus twice this, I get 3. -1 of the first guy plus twice this, I get 8, so on and so forth. Okay? This is not a miracle, right? Right? This is simply this very simple fact, right? That any dependence between the columns, right, corresponds to a dependence between the columns of the reduced row echelon form. Okay? When you do elementary row operations, you're not changing the solution set of the homogeneous problem. Okay, so that's what this is saying. Any dependence between these guys is a dependence between those guys, right? If I took column 1 minus, I'm sorry, 2 column 1s minus column 3, I get the 0 vector, and the same thing happens up here. Not a miracle, right? It's just simple logic. Okay. Okay. So. So now let's come back to the proof. Okay, so we want to show that the dimension of the column space and the dimension of the row space are the same. Okay. Okay. So let U. So let's continue the proof. Let U be the reduced row echelon form. Okay. Okay. And then notice that, observe that any column without pivots can be expressed as a linear combination of the columns with pivots. Right? I come down to the reduced row echelon form, and I say, oh look, any column without pivots, that's these guys, can be expressed as linear combinations of the columns with pivots. Right? This guy is twice that guy. This one is -1 of this guy plus 2 of that guy. Right? Any column without pivots is expressible as a linear combination of the columns with pivots. Okay. Further, the columns with pivots are linearly independent. Right. Further, the columns with pivots are linearly independent. Pivots are linearly independent because these are the standard basis vectors, right? It's 1, 0, 0, 0, 0, 1, 0, 0. Okay. Right? So what does that tell you? That tells you that the dimension of the column space equals the number of pivots. Right? Equals the number of columns with pivots. Okay, so that's exactly the rank. That's the same thing as the dimension of the column space, dimension of the row space. Okay, so right. So let me illustrate with the picture again. Okay, so coming back to here, what you see is that the columns without pivots are in the span of the columns with pivots. Right? This guy is in the span because it's twice that guy. This guy's in the span because it's -1 of this guy plus 2 of that guy. Right? So what does that tell you? That tells you back here that these guys are in the span of these two guys. Right? These two guys. And these two columns are in the span of these two guys. Okay. Further, we see that these two columns are linearly independent. What does that tell you? That tells you that these two columns are linearly independent. Okay. So in other words, the dimension of the column space is 2, right? Because these two, these are linearly independent, and these guys are in the span of the others. Okay. So that gives you that these two guys are a basis of the column space of A. Right? These two rows are the basis of the column space of A. Right? Because these two are in the span of it. Yes.
Could you say that? You couldn't say that.
You couldn't say that these guys are a basis for the column space of A.
Right.
They're a basis for the column space of U.
Right.
Right? But the column space of U is not the same thing as the column space of A. The row space of U is the same thing as the row space of A because doing the elementary row operations doesn't change the row space, right? But doing row operations definitely changes the column space. As you see, the column space here is nothing like the column space here. Okay, so yeah, do not say that these guys are a basis for the column space of A. They're not. Right? The corresponding columns are a basis for the column space of A. Okay. Is that clear? Is that clear? Right. So. Okay, let me have you do an exercise, just for practice. So I'll give you, here's a 3x3, 1, 3, 2, 2, 1, 4, 4, 7, 8. And I want you to find the find bases of the row space, column space, and null space. Okay, so take this vector, take this matrix, and do everything we've been talking about this class to it. We have only a minute or so left, so let's do it. What do you get when you do the row reduction on this guy? I hope you get 1, 0, 2, 0, 1, 0. Okay. So tell me something. Avery.
Sorry, how did you get rid of the 3 in the first row? Or in the first row.
With the 1 here.
Or no, in the first row, because it's 1, 3, 2, and then you have 1, 0, 2.
Okay, maybe we'll talk about it after. Let's just assume that we can do this part, and then we'll let me talk. Okay, so somebody tell me something at this point. You can tell me something, right? What can you tell me? Yeah. Mara.
Because you've got pivots in the first two columns, you know that the first two columns of your original matrix are bases for your column space.
Exactly. Okay, so you know that for the column space, you have a basis for it. The basis is 1, 2, 4, 3, 1, 7. Okay. Somebody tell me something else you can get immediately? Read.
The row space is 1, 0, 2, 0, 1, 0.
Great. So you know dimension. You know that you have a basis for the row space, namely 1, 0, 2, 0, 1, 0. Right? Okay. Everybody all right with that? Right. Okay. And then to find for the null space, you see that x1 equals -2 x3, and that x2 is equal to 0, and so this thing looks like -2, 0, 1. This is a basis for the null space. Right? Because x1 will have to be -2 of the last guy, x2 is 0, and the last guy is whatever he feels like. Okay. If you could do that, then that's good. Then you understood most of what we talked about. Okay. While you were doing the problem, I wrote up this thing, which is what I said over here. Right? The columns in this guy corresponding to the pivot columns here are a basis of the column space. Okay, so I said it, but if you want to write that down, that's actually pretty important. Okay, that's it for today. See you next time.